Hello everyone, my name is Mario Batubara. I'm coming from Research Center for Space Science at the Research Organization and Aviation and Space in Indonesia. So today I will talk about the optimization of array system configuration using the smooth path algorithm. So this is the outline of this presentation. At the beginning, I will briefly talk about the astronomy, radio interferometry, and the example of radio interferometry. And next, in the second part of this presentation, we found some problem in the general design concept, goal of design, and some previous optimization to solve the problem in the previous radio instrument design. And in the third part, so I will briefly talk about the basic concept of our proposed method and with some formulation and equation, and also to validate the algorithm. We use some data to get some comparison result, and finally, so we list some conclusion of our work. Okay, so I think, and for the introduction, we already know about the radio interferometry. So for the radio interferometry is an advanced technique developed by professional radio astronomers that allow to use many small antenna instead of a two large one. And the radio interferometry assemble an array of radio telescopes that work together as a rushing of telescope to achieve higher angular resolution. And up to now, there are a lot of example of radio interferometry, like a very large array, low frequency array, very long baseline array, as well as the square kilometer array. So basically, the measurement concept of radio astronomical measurement drawn in the left figure. So from this figure, the concept sketch of radio astronomical measurement using a correlator antenna. And the important thing is the brightness distribution in the angular domain is retrieved by the inverse Fourier transform of the sampling of its visibility in the spatial frequency domain. And the sampling point are determined by the autocorrelating the array configuration in the spatial domain. So in general, the concept of radio astronomical measurement is drawn in the left figure, and mostly all measurement using the concept of Fourier transform. So about the problem, so there is several problem in general design concept, and mostly of the general design concept use the grid system and discrete system. And the most important thing is the goal of the design is how to increase the sensitivity as well as how to suppressing the side lobe level. So to solve this kind of problem, some previous optimization technique has been developed, like aperture synthesis technique based on the cross correlation calculation, and the probabilistic technique use the simulated annual particle swarm autonomously and shifting technique. So all of these previous optimization techniques are basically use grid and discrete system, and also they are running in separately in each observation. So to to solve this kind of optimization technique, we found our proposed method called smooth path algorithm. So basically the algorithm itself shown in the left figure here. So this is the schematic view of our algorithm. So for example, we select some of the, the position of interest shown in the blue circle. So some of the antenna position grouped in one circle with the inside the kernel radius RE, and also we divide the kernel function and domain area, and also the center of interest path. So the advantage of this algorithm is mystery method that do not require connection between nodes of the area domain or a grid system, but rather based on the influence of its node with all its neighbors. So for the kernel function, plays the weighting role for node interaction in the accuracy scheme. So for the kernel function, we use this equation for the kernel function. So this kernel function, we use three kind of different situation as shown in this equation. So for the algorithm of our proposed method, so firstly we initialize all attribute path of interest and radius of kernel, and for the processing we calculate three calculation. First, the density of each part with this formulation, and we calculate the synthesized beam, and lastly we suppressing the side lobe level based on the Gaussian tapering. And for the fitness evaluation, we identify the peak side lobe in the 2D beam plot and evaluate the fitness condition based on this condition in the side lobe region. So for the data of our case in our work, we use the antenna location as shown in this table. So within the 8 location of the antenna, the important thing, we add one our future of radio telescope that will be located and installed in Timor, shown in this map, in this location of this map. So for the result, so we compare the distribution ratio in the UV coverage with snapshot and long-term tracking observation. For long time observation, we choose a 6 hour for our tracking synthesizes. So based on the comparison in the UV coverage, the algorithm can improve the distribution ratio at snapshot and hour tracking with the respect to about the 50% and 60%. And for the second result of our work, so we compare the side lobe level estimation based on the proposed algorithm with the peak side lobe level and average side lobe level within the hour tracking. So for the result, so we can suppress the side lobe level at the average and peak level with respect to about the 80% and 90%. So for the conclusion, so we have developed the smooth path algorithm to improve the quality of the simulated point source as the array configuration problem. So the proposed algorithm is able to distribute uniformly the UV sample in the spatial domain frequency, and also the smooth algorithm is proved to reduce the SLL in angular domain based on the array configuration sample. So although The algorithm of this will use a combination PLBI network in Japan and Korea, consisting of 8 radio telescopes with 20-meter diameter of each. The algorithm is designed to work on large samples for random geometrical shapes and for different criteria of radio telescope. So these are of our presentation. Thank you for kind attention.